Okay, let's go for chapter 3. That what we've got here for today, anyway, is going to be on coupling and individual joints, anyway. That what is said in here is the shaft for coupling is a machine's commonly used for transmitting the power from the driving shaft to other machines' components axially, such as the transmission of systems of an electrical motor to a pump. So therefore, it's mean this kind of thing is gonna be a shaft of the input shaft to the output shaft is gonna be in the manners of axially. So the coupling is gonna be in between the driving shaft and the driven shaft axially, things like that. And then that what is said in here, the transmission by using shaft coupling has advantages such as allowance of some minor misalignment. This means the driving shaft and the driven shaft might not be aligned to each other, not so much. Anyway, it's going to be some minors only of the axle assembly of the corresponding driving and the driven shaft respectively, and not and also it's going to include for reduction of vibration and overload problem, things like that too. So therefore, let's see the typical types of the coupling, of course. Okay, number one, there we have a rigid coupling, as its name implies already. It means everything is rigid. It's typically used for transmitting power from a fixed distance and will align of the driving to the driven shaft respectively. I would like to highlight for this one is well alignment. So it means everything got to be in the proper manners of alignment. It's going to be the most important things. And then for the set flexible coupling, okay, number two is used for transfer power of some minor misalignment of the axle assembly of the corresponding driving and driven shafts and can be able to reduce vibration. Okay, flexible coupling, things like that. And then we just typically gonna be some kind of like rubber type, things like that. Okay, I'm gonna show you down there. It's gonna be some kind of flexible coupling. It's gonna be look like that. See, this one is made of rubbers all the way. So that's why the driving shaft and the driven shaft, actually, things like that, even they have some misalignment, things like that. So therefore, if we apply the rubbers on it, flip between the driving and driven shaft, it can be able to allow to do so anyway. So therefore, this kind of thing is going to be the flexible couplings anyway. And then safety coupling is used for transfer of power from a driven to a driven shaft and can be able to handle overload problem. Most of the coupling is gonna be safety couplings anyway, because that's why I see if the overload come up, things like that for the driven shaft, so it's why the slip gonna be happening anyway. So or some sign like the bolts and now it's gonna be tears apart under the shears, I mean the failures and things like that. And then the slip coupling is used for transferring of power from driving to the driven shaft by using the slip friction principle. So therefore, we can just manipulate the torque by using the friction principle. If the torque is too much, things like that, they're gonna slip all the way. So the driven shaft will rotate with the speed of both driving and driven shaft almost equal. So it means the driving and driven shaft is going to be handle the same torque, things like that. And number five, controllable coupling is going to be used for transmitting power from the driving to driven shaft and can be able to control either torque or speed, things like that. So therefore, we have a gear, things like that. We have a figure there at the end of the chapter. I'm going to talk about this later, so anyway. So this way, it's might be control both in terms of the speed, the torque, things like that too. So let's see the typical types of the rigid coupling that what we're going to employ for this anyway. That what we have a rigid coupling, it's going to be easy to make installation, things like that. We have two of them anyway. One is going to be flank coupling, and then the second is going to be rib compression couplings anyway. We're going to go one by one then. The first one is going to be flank coupling, that what we've got here on figure 3.1. Okay, let's see together. So the figure of 3.1 is gonna be look like that. We're gonna have a driving shaft insert in here and then the driven shaft insert out there. Okay, and then we have a flank there and a hub there. we're gonna couple to each other by just apply bolts and nut together to fix this together. So this is the section views in a way. So you may figure it out. See the insert the shaft on the left hand side, and then the output shaft is on the right hand side anyway. And then this is going to be the front wheel anyway. It's going to have the bolts and nut, and then it's going to be the dash line here is going to be the pitch line, things like that. That what we apply the bolts around anyway. So therefore, this kind of thing, we're going to apply the keys also at the both shafts anyway, in order to allow everything to going to rotate to each other, things like that. So therefore, based on this, the flank cup we're going to employ a lot with some kind of like in the order to make an easy operation, things like that. Because it's why SME just be a lot of things that we're going to employ for the flank couplings anyway. Because why it takes less space, things like that to make installation. So therefore, this kind of thing is going to employ a lot with this anyway. So you may figure out all the dimensions appears in here. For example, like A, B, C, D, E, F, H, and L respectively. It's going to be the dimension appeared here is going to be the terms of the ISO, the Japanese Industry Standard or GIS, things like that. So let's see one by one. The first column there, it's going to be the coupling diameter is going to be the A terms there. Okay, this is the name of the coupling. For instance, we call the coupling names of 112. Okay, for the coupling diameter, and then the second column is going to be the shaft diameters. It's going to be the shaft diameter. Going to be insert in there. It's going to be the D there. So therefore the D there is going to be uh, the diameters of the shaft. It's going to be available both in terms of minimums and maximum. So it's mean based on this line anyway. It's mean we're going to design the size of the proper shaft first, and then we're going to make a selection on the coupling diameters respectively. So therefore the shaft diameters available as a whole there is going to be minimum and maximum respectively. You may figure out here. So the holes there is going to be the minimum, because that's why if we go down and bind a piece of coupling, things like that, okay, it's going to be just make in manufacturers in terms of minimum diameters anyway for the holes there, because that's why you can be able to enlarge up to the maximum things, because that's why the maximum things, for instance, like it said in here, the minimum is 16 and then the maximum is 25 thing anyway. So it's mean if you go buy it, it's going to be available for 16 and you can enlarge it up to the maximum of 25 anyway. So therefore, this kind of thing is going to make it easy for some kind of like a calculation, things like that. And then another one, the L term there. So the L term is gonna be the flank coupling thickness anyway. It's going to be the whole thing, the thickness of the flank itself, and then the whole thickness of the each side is going to be L anyway. And then the C terms there, the C terms is going to be the capital C is going to be the hub diameter. Okay, the C terms there, and then the B term there is going to be the diameters, okay, of the dashed line here. That's going to allow the bolts going to be through, okay, around this pitch circle anyway. And then F is going to be the terms that what implies in the sense of the flank thickness of each side. See, we got the flank of F on the left and on the right respectively. And then we have an edge term there. Okay, the edge term there. The edge term there is gonna be the flank, and then we just include the thickness of the rim part, or these small flanks up here, to just around allow the boat to sit down there properly to just protect the height of the boats and height of the nuts also. Okay, so therefore edge is gonna be the total thickness of the flank, whatever. Okay, that include the rim parts also. In K terms there, it's gonna be the terms of the thickness of the rim of the flank itself. Okay, I show you up there. And then N is gonna be the numbers of bolts. You may figure out there is gonna be the maximum is 8 anyway. So therefore, if you apply for more than 8, it's gonna be just less strength on the flank surface anyway. So therefore, the maximum of the holes there should be 8, whatever. And then A here, it's gonna be the hole. Just take some kind of like understanding here. This is the hole of diameters A here, and then you insert the bolts there, okay, inside. So you gotta be careful here, okay, because that's why if you got a bolt diameters of A and then you have a hole here is A, you cannot insert the bolt inside because that's why you gotta do some tolerancing. It means the hole here you gotta enlarge it by using the tapping machine, things like that. Using tapping machine, you tap it over. For instance, the tolerance of uh, 0.01 something to allow some kind of clearance to allow the bolt to insert inside, things like that. Okay, so therefore this one we call fitting on the machine parts, things like that. Okay, and then spigot and socket there to allowed here. Okay, spigot is mean the male one. Okay, and socket is gonna be the female one. Okay, it's gonna sit on each other properly, things like that, to allow the assembly to be some kind of like alignment, things like that easily. So therefore, the spigot and socket is going to E is going to be the width of spigot and socket, and S is going to be the length of S2 and S1 respectively. S2 is going to be the height of the spigot, and S1 is going to be the depth of the socket respectively. Okay, and then our term is going to be the terms of fillet radius here. I just explained to you guys before the machine parts. Okay, we're gonna round it up by just apply the fillet radius there. Okay, so therefore we round it up for the fillet radius of R and C respectively. Okay, so R there is C is there. Okay, both of them is gonna be fillet radius anyway. Okay, to just I mean erase the sharpness or make it roundness anyway for the machine parts, things like that. Okay, and then let's see on each line there. So it's mean the flank coupling is gonna get started from the 112 up to 335, or it's applied for the shaft diameter sub 16 up to 100 only, things like that. So it's mean okay if you just go for the shaft diameters just more than 100. It means you got to do another way around. For instance, you gonna be able to find another solution. For instance, like you can apply for the chain transmission, the belt transmission, or the gear transmission system, things like that, rather than the coupling, because that's why the coupling is too big and the amount of the weight is going to be too much, things like that. So that's why it's going to handle for the shaft, things like that. The shaft going to be applied for towards loading. It's going to cause a lot of failure to the bearing consequently. So therefore, you got to be careful with this anyway, okay? But of course, in some cases anyway, you got to you're forced to do so to enlarge more in terms of the diameters of the shaft, things like that. So it's mean you got to do some kind of design or manipulate the dimensions all around here by yourself. It's mean you got to, okay, you got to do the in the extrapolation. For instance, like, okay, I go for 130 millimeters shaft diameter. I insist to do so with the coupling transmission system because that's why I have no space available anymore. So therefore, no doubt about it, I forced to do so. So therefore, okay, I just manipulate the size of the L term there. So that's why I just make extrapolation. It's going to be what? 100. The L term is 125. So that's why 130 is going to be 125 over 100 times 130, things like that. Okay, so that's why everything can be extrapolated. Okay, and the maximum numbers of bolts there is going to be 8 all the way. It's going to be fixed there. Okay, and then the bolts and nuts, the A diameter there, you got to do the bigger size of the A of the bolts available. We're going to talk about it later, so what? Okay, but all dimensions of L, C, B, F, H, and K, things like that, you can do extrapolation. And then let's go for the manufacturers, okay? Do the fabrication of the flank cupping here. We can do both anyway. So both of them can made of cast iron. It means you're gonna make a mold on it. Okay, so that's why you gonna um, just heat it up for the iron to be in the liquid phase, and then you just pour it in the dyes, things like that, and then let it cool down. So that's why you got a piece of the flank couplings in a way. So that's why another way around, you can do both of them together. So this one is made of cast iron, of course, it's going to be brittle metal. And then another way around, okay, it's available. You can go buy it, buy the cast iron, things like that. And then another way around, you can make it up by yourself, okay, because it's why this is going to be easy then. For instance, see, you just cut, okay, the flank itself, okay, by the gas welding cutting machine, things like that. Okay, you cut it in a round manner, and then you grind it together, whatever, and then you just apply, okay, for the pipe, okay, a hollow shaft, things like that, and then you just weld it up together, things like that. So this way you got a piece of the flank, things like that. So you got two pieces, things like that. You coupling to each other by the bolts and nuts, based on this. So therefore, if you just fabricate it by yourself, things like that, it's gonna be made of mild steels all the way. Okay, this is the thing that we can do both in a way. But most of the time, you can either go buy it with the casting machine, things like casting coupling, and then you can do it yourself. Gonna be in terms of the mild seal, things like that. Okay. And then another component that what we're gonna use for is gonna be the bolts and nuts washer. Okay, let's have a look at it. This is the bolts. Okay, this kind of bolt is gonna be have an A here. The A here is gonna be corresponding to the hole in here. Okay, it's gonna be exactly the same. So therefore, that's why I explain on it. The diameters of A here, you're gonna do enlarge it by just using tapping machine, things like that. Okay, to enlarge it. Okay, and then this one is gonna be the same age there, and then the thread. Okay, of the bolts there, we have a D. So D term here is gonna be the nominal diameters of the thread, things like that. Okay, so therefore the thread is gonna be only on the portion of S only. Okay, so this type of bolt is going to be special for coupling design, things like that. So the names of it, we're gonna have, see, for example, the first line there, the smallest one, 10 times 46 is mean the holes there is 10A. Okay, the A is 10. And then D1, okay, the D1 is there, okay, it's gonna be the nominal diameter of the tray. Okay, it's different. Okay, and then it's mean you're gonna apply the bolt for M10, things like that. Okay, and L is gonna the length of the bolts, things like that. Okay, and then you may figure out there. So M12, A is 14. It's different, huh? And then M16, so A is 16 also, and M20, so A is 20, and then M24, and then A is gonna be 25 millimeters, respectively. So this one is going to be the associate parts. And then the nuts there, okay, we're going to apply on it to just make some kind of clip the flank capping on the left and the right together by just applied on it. And the washer here, you guys may recognize, see, the washer here is going to have a duty to increase more just F sub I on the thread, right? Remember that? So therefore, you can tighten up more. So that's why the F sub I in the bolts here is going to be more. So therefore, in order to loosen, you can need to apply the torque on the nuts here to take this assembly out. So that's why this is one way or another to do some kind of like awareness of the protections of the loosings of the boats, or in Thai language we call it ป้องกันการคลายตัวของ knot, things like that. Okay, so this sort of thing is going to be the things that what you can keep in mind. The watcher here is going to increase the FSI, things like that. Okay, and then just for the material, okay, that what I mentioned earlier. So that's why the flank capping can do either by cast iron, okay, with the sigma U of this, and then the either for carbon steel, things like that. Okay, you can make it by yourself, and then or you can do is used by the Fortune carbon steel. Okay, this one also the sigma U and sigma Y respectively, and then for the carbon steel, okay, this is going to be high carbon steel, things like that. Okay, and then the bolts and nuts. Okay, we're gonna have a hot roll steel SS41. It's gonna be Japanese code anyway. We have a Sigma U and Sigma Y respectively, and the washer is gonna be high carbon steel respectively. And then let's go for another terms. It's gonna be the standards on the flank coupling anyway. Okay, let me read it out for you guys here. It said it here, based on the Japanese Industry Standards or JIS. The numbering system of the flank coupling uses the number of standard cord and then followed by the outside diameter of the flank coupling time the shaft diameter. If the shaft diameter of both sides differs, each diameter have to be identified and the metric being used respectively. In addition, the speaker and socket are also added by the letter M and F respectively. It means speaker is male, M stands for male, and socket stands for female respectively. For example, okay, the first one there, JASB1451, things like that, is going to be the code of the Japanese standards of the fan coupling. 140 here, it's mean the flank diameters, okay, the coupling diameter is going to be 140 and the shaft diameter of 35. The material being used for this is going to be FC20, things like that. Okay, the Japanese steel, things like that. Then 180 times 50, things like that. Okay, A is 180 and then the shaft diameter is 50. It's made of material of S25C respectively, and then 200 times 56 MF, and then SF45 is mean. See this one, the flank carbon diameter is 200, the shaft diameter is 56. We have male and females also, or the speaker and socket to allow to convince for the assembly and disassembly on the flank couplings anyway. And then, so this one is going to 160 times 45. It's going to be 8. It's going to be 160. And the diameters of the shaft is 45. It's have a male on one side, another male, another female on the other side. Okay, speak on the socket. And both of them made of the material of SC42, respectively. Now, let's go for the transmission system or the force acting on the flank couplings anyway. So, okay, let's have a look at the figure 3.3 there. Okay, on the left hand side, it's going to be cross section. We have bolts there. So we tightened up the bolts. It's going to have F sub P there to compress the flank coupling on the left and on the right to stick together. So F sub N is going to be the total force applied by the bolts there. So F sub N here, you make a note on it, equal to N, numbers of bolts, times F sub B respectively. And then on the right hand side, okay, we have a pitch diameter there. We have 1, 2, 3, 4, 5, 6 of the bolts there. And then we're gonna have, okay, these two plates have been attached to each other. We're gonna experience the friction force, the F sub F there. And then the F sub S there is gonna be opposite for the direction of rotation. And the torque generated is gonna be the direction respectively, and the diameters of the pitch is gonna be D sub B. So therefore, in conclusion, okay, the T terms there is going to be the torque applied, okay, or transmission torque from the left to the right, okay, should be, okay, should be okay less than okay. So that's why this one is going to less than the torque sub F. So the torque sub F is going to be the friction torque then. So based on the figure on the right hand side, F sub F times D sub B over 2 is going to be the torque then, torque sub F. So we just substitute F sub F by F sub N time mu. Okay, so therefore it's going to be it then. And then, so this one, okay, we just be able to find, okay, what happened if the torque input is going to be greater than the torque sub F. It's going to slip, right? It's going to slip. So the maximum torque is going to be only the theta, okay? And then for the more emphasis in terms of the generation of F sub n and F sub b, the relationship turned out to be F sub n equal to F sub b times n there. So therefore, we make a substitution. So that's why we get a formulation there. And then let's see the F sub b. Okay, this is a trait. Okay, the thread connections in a way. Remember that? So F sub b just estimate to be F sub I gotta be equal to the sigma y times A sub s. You should highlight the terms of A sub s, please. The A sub s is gonna be the stress area of the boat. Remember that? You got to find it, okay, with the applied of the bolts and nut fixation, things like that. So therefore, it means you got to just find the A sub s based on the text number one, okay, anyway. So therefore, this is the thing that what you should put on it. And then therefore, okay, the things that left over is going to be the table 3.1, the design of fan activity done by making selection of fan coupling according to the size of the shaft. However, the selection should be done based on the standard of fan coupling which show in table 3.1. That's what I make explain on it already. And the terms here is gonna be allow you guys to know about the mu statics and mu dynamics. Okay, so what does mean by dynamic is almost just slip there. So therefore, this one, if the material is made of steel, both of them, okay, you're gonna have if you're gonna go for dry. Dry is means not lubricated. Okay, wet is mean it's lubricated for the both and nut, things like that. And then so therefore this is the steel, things like that. And then the steel and cast iron, okay, based on the brass and bronze, things like that. You have the same uh, coefficient of frictions in a way. So typically we're gonna design with the static friction, okay, as a basic things for the design, because it's why the static thing is gonna be it's much more, okay. So therefore we can take the more force involved anyway for the calculation. And then another one is going to be rep compression coupling. Okay, the machine's going to look like this. Okay, you're going to have the left hand side is going to be just section along the shaft. The input shaft is on the left and the output shaft is on the right. So this one we grip together, okay, with the rip compression. So we mean we're gonna apply the bolts on the left and on the right together to fix, okay, to just grip, okay, the two shafts together. Okay, it's just gonna be look like that. So therefore, this is the standards of the German machine. The German machine just use a lot of the compression coupling. So therefore, based on the standards of the DIN, okay, I mentioned about DIN before. This is German standards. It's gonna be pretty high standards anyway. So again, okay, so the shaft diameter is gonna come first. So that's why it's mean you got to design everything down with the shaft diameter first, okay, and then you're gonna have the approximate weights available so of the system there and the torque there and then the D sub A and L. Okay, D sub A and L, you may find it here. D sub A is going to be the diameters of the rib compression coupling and L is going to be the length of the lip compression couplings respectively. So therefore this is the things that what I play for the rib compression. And then the calculation again, the torques there. Okay, we can make a calculation of F sub B times N times mu times D over 2 respectively. So this is going to be the fast and force of the boat. It's going to allow you a lot with the F sub B, things like that. Okay. So therefore, this is the things that what we gonna use a principle as a design. Seems like everything's gonna base on the friction principle anyway. Okay, now let's see for example 3.1. The 3.1 here is that the flank coupling as shown in figure 3.1 have a dimensions as follows. The cavity is 75. This means the shaft diameter is 75. And C is going to be the hump diameter is 136. And L is going to be the length of the whole flank on the left. Okay. And A is going to be the hole. Be careful here. The hole right there at the flank coupling then. And B is the pitch diameter that you just insert the bolt to fix around. And then F is going to be the flank thickness. And given that the solid shaft is made of steel having sigma y of 524, bolts and keys are made of material of sigma y 450. The flank coupling is made of the steel having a sigma y of 4 or 6.8. Numbers of bolts is 4. And then this should be careful here, this statement. It said here, and the safety factor gonna be used of 3.5. Okay? So therefore, we said here, determine the safety factors of the corresponding machine parts when the maximum torque determined from the solid shaft is used as the torsional loading applied to the flank couplings. Anyway, so it's been, okay, we consider like this. It's going to turn another way around rather than the things that I make a lecture a while ago anyway. So this one is not the friction principle anymore. Okay, we forget it. It's mean, okay, we got to have the whole system comprised of from the left hand side. Okay, we have a shaft, input shaft there. We have a left flank, okay, and the right flank. We grip together with the bolts and nuts. And then we just have the output shaft on the right hand side. This one we just consider everything as a whole piece of metals, whole piece of machinery, one piece only. So therefore, I'm thinking about, okay, I apply the torque on it through from the left to the right. Anything damaged or not, things like that. That's what we call here is well-fitted machinery. Okay. So therefore, again, I would like to emphasize here, the consideration here is going to be all the components gonna well fit to each other assembly, and then therefore we think about the machine considered to be as a whole unit when we just transmit the torque through things like that. Everything's gonna be determined any damage or not. Okay, if just like this, we go ahead. We just only have the force applying on it's only the torque. So therefore the stress induced is gonna be the shear stress only. So therefore this is the simple stress. So therefore we apply the power supply is 0.6. The shaft is made of material, one material, the bolts and key another material, and the flank coupling is going to make up the non-material. So that's why we got the power supply of each of the members respectively. And then so therefore the maximum torque that can be able to transmit as a whole member from the left to the right from the input shaft there is going to be determined like this. The torque going to be equal to town design. The town design is going to be given by the problem set of the input shaft is 314 over given the safety factor is 3.5 and then pi d to the power of 3 so over 16 respectively. So therefore, we have the torque generated is going to be 7,441 respectively. Again, now, from this point of view, anyway, it's mean we gonna consider the whole system as one piece. Anyway, so therefore, the torque gonna be transmitted from the left, from the shaft on the left, through the crank coupling on the left and then passing to the bolts and nuts, okay, and then to the right flank, and then just to the output shaft respectively. We're gonna watch over any damage on the each component parts or not, okay. So therefore, let's get started. Okay, I think about the failure may occur. Okay, I said may occur at the bolts. So damage is gonna be right there at the bolt to the shearing stress. Is mean. Okay, when we start the engine, everything's gonna be tears apart by the shear force. Things like that. All the bolts gonna be gone. So therefore, in this kind of sense, see, we got a boats of M20. Okay, the promises have say anything about the M20 at all. But the holes there, A, the small A here, right? The small A here is manipulated to be 20. So that's why let's get back there from the table 2 here. That's what we've got here. It's mean, see, when we have a of 20 there, so therefore, okay, the bow is 20 there. So therefore, another A in here is 20 also, okay? So therefore, this one is going to be the same thing that what we have got there. So that's why the hole there is available. So that's why we pick up the boats of this one, of this one, of this one, okay? So this one is going to be M20 all the way. See what I mean there? Because that's why this is gonna be the things that what manipulate for the hole right there in the fan couplings. That's why we're gonna pick up the choice for the bolts we applied on it. Okay, that's why we're gonna apply for M20 there, and then we're gonna enlarge the hole, do some tolerancing, manipulation, and so therefore we got there available. Okay. And then, okay, that's what we've got here already. So therefore, I got M20 on this line, okay, and then I got 4 of them. So that's why the stress area is going to be pi over 4 times 20 to the power of 2, things like that. So therefore, the shearing force can be determined as F times tau side times A, things like that. We just put the tau term as the unknowns anyway. So therefore, the arms of the force is going to be right there at the B over 2 there. So it's going 1 over 5. So that's why the torque equal to F times R. I just substitute down there. F is going to be 125, 1256.4, and then times by R, things like that. So that's why I got one unknown left there. This means I just input for the torque of 7,441. So after I just induce the torque of 7,000 something there, so it means I experiencing the tau term in each bolt of 56.4. I check it's going to be damage on that then. But the safety factor is mean I got 4.8. Everything's turned to me to be alright then. Okay, and then the next one, failure may occur at the bolts and the flank due to the bearing stress. So this is the bearing stress induced right there at the contact of the bolts and the flank. So the bolt hole is A, okay, the flank thickness is F, and we got 4 bolts there, we times by 4, okay. So again, okay, the force is going to be equal to sigma C times A, and it's going to be the arm is right there, it's going to be V over 2, and then the torque again is going to say 7,000 something. I find the stress induced right there at the contact area, either at the bolts and the flank also is going to be 32.8. So that's why I check the safety factors turn out to be 13 and 12.4 respectively. It's under safety condition. It's going to be much more than 1. Okay, the safety factor, so no problem. And then another one, failure may occur at the hubs of the flank of the coupling. Okay, this one is going to be right there at the surface of the bolts there. See, I mean figure out there. So we have a flank, okay, and we have a hub, okay. So that's why this one is going to be pi c. Pi c is going to be the I mean the what do you call that? The peripheral, the diameters. I'm sorry, the perimeter, perimeters of the circles anyway, and you time by F is going to be surface area. Okay, so this is going to be the surface area of the hub. Okay, in the portion of the flank. Okay, this is going to be the age. So therefore, again, the force is going to be pi times tau times c times f, and then the r term is there, and then again I have to input the torque of 4,000 and something. I find the tau term is going to be 9.48. So that's why it's going to be safe with a safety factor of 25. And then another one, failure may occur at the keys. Okay, this is why the shaft diameter is 25. So this is why in the chapter that what we talk over for the key design, we pick up the rectangular key, okay, of 12 times 12. Okay, you just go for the chapter of the key design. Okay, and the length of the key should be equal to the hub length. The hub length is here is going to be manipulated to be 120. So therefore, we just find the safety factor under the shear stress, okay, of 3.3, and then the safety factor of the key under the compressive stress is going to be 1.6 respectively. Okay, again, it's going to be glad for me to have a look at the safety factor that what we've got here. So this way, the smallest, okay, safety factor seems to me is going to be right there at the key. Okay, so therefore, if the overload problem happens, either on the driven shaft, things like that, so therefore, the most likely failure is going to happen right there at the key. So the key is going to be tears apart. So therefore, everything's going to be free. Say after this, it's going to be safety matters of the designs anyway. So this is why if we just solved all the problem already, and then we can replace a new key in place. So that's why everything's going to be run. I mean, normally again. Okay, this is the things that what you just keep in mind on that. Another type of coupling is going to be have a rigid shaft coupling. Another type there is very similar to the rigid coupling that what we just have it a while ago anyway. And then we have the rubber type that we mentioned about it. It's a rubber type there, and then we have some kind of like a gears for controllable coupling, things like that, and all the loader chains, coupling like that, and then the reverse joints, things like that. You can design, okay, both of the side at the front and on the rear one. It's going to be a couple to each other, things like that. Okay, you can decide what the joint and the stress induced in each of the members there. Okay, so therefore, in this chapter, okay, I'm gonna be end up for my lecture today. I have the problem set of 1 and 2 and 3. Okay, let's see. Okay, for the problem set number 3 here. Okay, I said here the flank coupling is connected between two solid shafts and having the diameter of 130 millimeter. Okay, first thing first, see this one. I ever put this kind of problem set as in the exam before. So this one we are forced to do so, okay, to use the coupling is bigger than 100. Because that's why you see this one you just been advised to use the table 3.1 with the maximum diameter, okay, of the shaft of 100 only. Okay, 100 only. Okay, 100 only. But now you are forced to do so with the shaft diameter of 130. So therefore, everything's turned out to me. You are forced to do so. You can do that. Okay. So therefore, because we have so many limitations on the space, things like that, we are forced to make some kind of like transmission system with the coupling manners, things like that. So therefore, we gonna do some extrapolation, okay, of each of the dimensions appears in here, okay. So therefore, that what I got there has been recommended by this problem set that, okay, we have the material of the steel anyway, okay. The coupling is made of steels, 140, and then we have 6 of M284, and the pitch diameters is 305, okay, the B term there, okay, and then the flank thickness is 38. I'm on the shaft, I use a key, okay, it's the material of the key. And bolts and nut are made of 1030 C steel, and then the safety factor recommended to be used is 4. Okay, number 8. Determine the safety factor of the associated machine parts when all of the assembly are well fitted. So therefore, I put that under parentheses. The maximum torque used for the calculation is determined for the solid shaft. It means like this. It's going to be exactly the same determination that what I mentioned earlier, right? So everything is well fitted machinery. So that's why we do a hole in the same manner. That we pick up the right bolts and nuts things like that to fix it. So that's why we can determine everything's gonna turn out to be one piece of machine component. So therefore, we do exactly the same calculation as appeared in the in the in the example there. Okay, you may kind of practice on it. And then in B, determine the safety factor of passenger part when the assembly are not well fitted. For instance, see, you got use M20, okay, rather than M24. So therefore, the things that what turn out to be from the step of calculation, you can be able to transmit the torques of, okay, the torques only with the torque of the friction force. Okay, so the torque here is going to be the terms of the F sub B determined for M20 only. So if just like this is mean, okay, you just put the wrong, okay, bolts to fix it. So therefore, anything to be happen with the shipment or slightly, okay, slip on the surface, things like that, it's mean the failure already happened. Okay, this is the thing. So that's why the maximum torque going to be applied on it is going to be this equation, and we can determine all the things with the torque, things like that, and then the safety factor on each machine component in a stepwise, like in example, anyway. Okay, please, okay, practice it by yourself, things like that. Okay, as the example that what I show you up there with the prompt number 3 there. Okay. And then number 4, you can just do it by yourself, whatever. Okay? So this is going to be it for the calculations of the flank coupling anyway. Okay? I'd like to stop it, okay, for my lecture for today anyway.